Okay, we are going live and we are recording at the same time. Is my audio coming? Oh, this thing is not recording my audio. The live stream is now getting my audio. Let's. There's probably not enough space for me to do the entire data bus between the dip chips. Yep. Probably needs to be redone, or I can use these size or these size. Let me try a new idea. Do this. After that, go back to this. Do this here. And after that, go back. You bros, right? Yeah, so true. That is so true. Come on. This is not working because if I want to do this, I'll just spread things out in the chip region. But here is an idea. Delete these, delete these, delete these. If the via is actually closer. Most errors 10 components go through them. When you're doing something this big. Yeah, absolutely. There are tricks that I have used during the placing of this PCB. For example, there is like 74LS00 chips. Let me check whether my audio is coming through. Can someone in the stream tell me whether my audio is working? Yep. So I'm busy routing this thing, so I don't have the time to show it, but I have used some very, well, let's say, I will not say unusual or trickeries. I don't know how to describe it. I've used some tricks to simplify the design of the circuit board. For example, when you say there's a 74LS00, like quad NAND gate that everyone know and love, the 4 NAND gates on the chip are all equal. So what you can do is you can swap the order of those gates around so that your traces don't cross each other. And that simplifies the routing a bit. Put the through holes D0, D3 closer together. That's an idea. But the problem is, so look, D0. I'm routing with a 0.02 inch grid. Let me say, set the language to English. Set the English to language. Yeah. I'm routing to a 0.02 inch grid. And between the lines, there are like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There are 10 grids. And each of those D0, D3, so it's like I am expecting to put the D4 via here and D5 here, D6 here. So each one of them is like one grid unit to the left, except for the first one, because I don't want to push the line one more grid to the right. Although I can probably, it's like it's not very working. So that is that. Yeah, why don't I? It's D4, right? Oh, I don't need BS here. Let's see. Oh. Uh-oh. Yeah, this is not looking good. Probably this is the best you can copy. Not bad. Things seem to be working. Why does that need to go there? Okay, that just goes there. U19 is an 8-input NAND gate. And I swap the inputs around to make sure the routing is as short as possible. Because all of those inputs are equal. Hey, before this live stream, I legitimately don't know whether it's possible to get the data bus through the middle of these chips. Turns out you can. As a bonus, I don't have to use both sides of the board. I'll push around the wires later. Which is a bonus because look at the amount of wires that need to go across the data bus. The hope is that there is not excessive interference. This board is going to work at something like 60 megahertz, maybe. So it is not like high speed signal, but it's borderline high speed signal. So probably there's no need for like proper high speed signaling designing, for example, like an oil copper core in like inner regions to create strip wires, impedance matching. None of those stuff is necessary, but interference may cause trouble. Power rails on the left so big. Like BG. Oh, okay. That grid of that is this is a prototyping region. This is a prototype. So it's like you can put sockets here and bodge wire to the board. Because this is a circuit with, I will look for, yes, U41. This is a circuit with 41 ICs. And this is the first design. And it has like 10,000 timing intricacies that may go wrong. So in these regions, I was like, there's no red lines going through them. I'll just put prototyping region there. So if anything goes wrong, I can add chips here, I can add chips here, I can add chips here. But not here, because the card may extend to this region, and if you put chips here, it may interfere with the card. So I'm putting maybe some logo here, like KiCad has an open source hardware logo, and if you don't know, this project is open source hardware. Just put it there as a placeholder. The the power is not, the power lines are not about the current. Like, I've calculated within like reasonable temperature rise, these power lines can carry something like 3 amps of current. So it's absolutely excessive for these purposes. But the thing is, I don't have a ground plane in the middle. And the TTL or CMOS chips, when they turn on and off, there will be a surge in the current consumption. So when this thing is running, there will be a lot of current spikes in the power lines. And if the impedance of the power line is big, then you have like fluctuations in the power voltage, and excessive fluctuation or noise in the power lines may cause trouble for the board. I heard this from the Commander X16 project. They had like excessive power, like noise problem, and they sort of just throw their hands up and use a 4-layer board. That's the story I heard. But for now, I'm saying, you know what? I'm going to dream big and use like a 2-layer board and use super wide power lines to see if that problem can be mitigated. Okay, let's do some simple routing. Very simple. That's why, yes, that's why we always have little caps. I had some reserve caps here, and there are some space like between the ICs that I actually can put caps. But I don't want to say, okay, I'm going to put caps here, and when I do routing, I was like, I need that place to route a trace, and then it's like, oh, there's a cap. I can route through there, and then basically I don't want to shoot myself in the foot by placing the filter caps or bypass caps like too early. So the current plan is, if there is some free space, maybe there's some free space here or something, I'm going to put some caps, but I'm also going to prioritize where there's a lot of logic gates. For example, this region. Like these chips is what you see, probably these ones, maybe not this one, as the protection in the schematic. So these chips are the heart of this board. It's what makes this board like a protected mode Z80 computer. And these part is just to generate a wait state. I use an excessive amount of wait state just for this. You can flip a switch and set the wait state it insert to your board. So this is a helpful feature if you are prototyping a hardware, like a new add-on card to this thing, and say, oh, I have a new sound chip. I want a Yamaha FM chip. I want to put in this thing. And I'm going to have a wait state generation circuit on the board, but I want to know how many wait states do I need to generate. And you can buy one of these. This is like the developer edition board, like the first version of the X16. So it's aimed at developers who can buy one of these. You can put your car on the board, disable your onboard wait state generation circuit, and you flip the switch and see when things start to break. And if you find out like 99% of chips work with 6 wait states, and then you can hardwire your onboard wait state generator to generate 6 wait states. There are a lot of things that can just be thrown away, like in a later version of the board. And like most of these parts is going to be replaced with the XC95144. It's a Xilinx CPLD. It will do address decoding. It will do like state machines. Basically, it will do the protection. And the reason why I chose it is because it works with 5 volts. So the roadmap is laid out, but the PCB is not. Let's see, what's the next part we're going to tackle? Let's go with the hard part. What is U23? I'm running dual screen here so that I can see the component on that screen. I'm going to put it here. Okay, U23 is this. So 1, 2, 3, 4, 5, 6. This is 1. And this is 1. So 2, 3, 4, 5, 6. So that is connected to there. That is connected to there. That is connected there. That's to that side. That's to that side, but this is to there. Probably what we need to do is to swap these so that the right unit doesn't have to connect to a bunch of things in the left, and the left unit doesn't have to connect to a bunch of things in the right. So when you see like minor changes to schematic to like simplify routing, if you go to the like GitHub page of this project, there's a lot of minor changes to schematic. That's what this is referring to. It's like swapping gates around, swapping units around. To make like routing a bit simpler. I'm not routing with a bit constrained. I like to round with like 0.05 inch. That, in my opinion, just make things a bit cleaner. But the rule is like the first lines that I placed there's a high chance that this is just going to be replaced. Hmm. I want to kind of exhaust the short connections first, and then start doing the longer ones. I'm using a via here. Because normally it's like, for long traces, one layer is for like horizontal and one layer is for vertical. Oh, CPLD, yep. I'm not a pro at CPID either, but I would say that the Xilinx one looks not bad. I'm not even going to say good, but it looks not bad. Some of the ones labeled H for high, are power. For example, these ones are power. But these ones are input that are just pulled high. So I'm going to connect to those with like thinner wires, just in case I need to cut these. And they don't need to provide like a bunch of power. Remember what I said about like horizontal and vertical wires? Here we go. Here we go. That's nice. That's nice. Okay, I'm going to be lazy once and see if I get away with it. Probably not. Probably not. Like, the next line I see is the read. It needs to go there. It does work going from there. Why does that look like that? I have absolutely no idea. Okay. Probably need to bring this over a little bit. Oh, because that is not parallel, I cannot actually get through that. The way to go is probably use the other layer. Oh! Oh, come on. Come on. On CPU. 170. What is the ISO? Okay, for this one, probably need to do a via. It's not a big problem. I need to follow my own advice about not routing long red, which means front horizontal lines. Full bit decoder, everything in microcode. Three general purpose registers. That's interesting. For 16-bit. Three general. That's It's either a RISC-V or MIPS style 0 register, or it's an 8080 style memory mapped register. That's the only way you can have something like 7 registers. It's quite a non-standard number. I keep typing X and V in the chat because V is for via or switch layers and X is for routing. Oh my goodness! Oh, whoa. What line is this? Oh, Steam Pie! Oh, hello! I did not recognize you. Tiny tape out. Everyone's talking about tiny tape out. I am probably going to try tiny tape out at some point. Maybe for like the protection circuit on like the HEC. Like on this board. Or the APS. The graphic system or the APS. It's kind of like the ULA. If you think about it. It's like Sinclair, they did the ZX80 and say we want to save some cost and we want a really low cost ASIC like solution and say, hey, UIA. Okay. Just going to do some lazy routing. Because why not? No operation. Registers addressed by 2 bits. Because I need to know. No operation. Silicon bus shall live forever. By the way, if I want the easiest routing, I should just do this now. Are these aligned to the grid? Okay. Oh, yeah. Okay. Here comes the problem. No op. So it's a no op register. let's just stick with that for a little longer. Bring everything to here. And we are probably starting to use vias because these are going to be oh, come on. Vertical routing. I will regret not using the front side for routing the other things. Okay. Let's see. That's 2. Say D3. Doesn't look too good, but it will probably work. This really is. There's one interesting thing here. And there's one trick when you design your own computer if you have SRAM chip. With DRAM chips, because it has something to do with refreshing, so you have to be more careful about those. But for SRAM chips, all the address and data bits are the same. So if you look at my data buses like D1, D3, D5, D7, D6, D4, D2, D0. It's a mess. It's a messy order of wires. But if you look at the PCB side, you have D0, D1, D2, D3, D4, D5. So you can always choose the order of data bits that are most convenient to route. Because the data will always be read out in the same order they are written in. So it doesn't really matter as long as you don't do something crazy like use the S100 like single directional like data in and data out bus. In that case, you need to keep like the input and output bus in the same order. Is that designed from Minecraft? Because Minecraft wire all everything. Interesting. Views 36. Concurrent viewers 6. I'm surprised that I get any viewers for the stream. That's just like, hey, I have this idea at the moment. Yes, I know we are going to have problem doing things like this. Of course. This is electrical engineering. How dare do I think... come on. Should redo all this. How dare I to think that I can be any lazy at any point? No. No. Let's hack a Discord. Yeah. I think a lot of people like find me on from other YouTubers. For example, like the protected mode, that thing got close to 600k views on YouTube before it went cold. And earlier this year, that video suddenly started to blow up once again for no obvious reason. And I was like, why? That is an old video. And it turns out that no one have made a video about the madness of the Z80IO, which is the twisted bus design. There was once a revision of the HEC, or hack, for short, that has a bus twister. Basically, it will twist the bus for I/O, will make the high address the low address and low address high address. And that is to use the string copy command, string I/O command, the not LDIR, INIR and OTIR, and there's OTDR and INDR, I think. To use those instructions to copy between memory and I/O fast. No, it's to copy between memory and memory fast. Because there's one very weird design in the HEC that have I/O mapped memory. That you are reading from the I/O port, but the memory will return the value. It's not on this revision of the motherboard. It's just too crazy and risky and hard to program to put into a first version design. But trust me when I say it does have its use. So when you do the I/O map memory, the bus twister will speed that up by a little bit. But then it needs to connect like 8 address pins to 8 address pins and 8 address pins to that. And you need like 4 DIP20 gates to that. I was like, nope, throw that away, and the bus twister just disappeared. But the thing is, Noel's Retro Lab did a video about it, and that video blew up, and it went on Hackaday, and the Hackaday news mentioned you can check out this video or this article that uses some trickery on the Z80 I/O system to implement a protected mode. And that links to, I think, another Hackaday article that has a link to my video. And that video just blew up once again, and it has now got more than 700,000 views. So yeah. However, SDR uncopy. It is. The every CPU that's derived from the Z80, that's including the 8088. If you look at the 8088, it kind of copies a lot of idea from the Z80, but it does have a nicer instruction set. I am a Z80 guy, but I'm saying the 8088 is a cleaner version of the Z80, and it has a string copy command, a string copy instruction. So, yeah, that is that. You definitely have that protected mode video. You haven't watched that? Seriously? I thought that everyone who'd ever even bother to check out this live stream would have watched that video like more than once, maybe. So it kind of surprised me when I say, yeah, I have that video on my watch later. Oh! Are you serious, KaiCat? I can push this through here, but then these wires will be off the grid. I mean, the grid is just to help you. So if they are in your way, you can just ignore them, but I like things to be on the grid. Found my channel like 2 days ago. Wow. Guess what? This one had to go to the front. But the problem is, if it goes on the front, and then will it will fit with asterisks. Okay. I'm not liking it. But forcing everything to be the way you like them is not the way to do electrical engineering. I'm going to see. Now this looks much better. Why can't I do this with that? Okay, I can. Just not with this one. Okay. Okay, fine. Circuits, sometimes they have a mind of their own. You got to respect their life choices. Some of the routing are super easy here. For example, this one. Comparing to how do I route this? Okay. This is just so standardized. You can copy these. I'll just copy 2 of them at a time. Am I connecting the same wires? Right. Yep. Not this one. So, yeah. Okay. Again, some of these routing are simple. I somehow find myself bolder with like routing when I'm on a live stream. Just somehow. When I'm not on a live stream, I was like, well, this conflict with that line. Well, it go across that line. I go live stream. I was like, you know what? There are viewers who are waiting for me to play that route. Let's try that first. Yeah. Not a lot of lines are crossing here. I can probably place some filter caps in there. Huh. Interesting. These are X. Why does U24 have X's? There's an X there. Is that X? So it's two inverting output that's not connected to anything. Then it's quite simple. It's quite a simple task that requires a via. It either requires a via or require taking some risk. And by taking risk, I mean routing a red horizontal wire. Let's go through the X region. And then via here to that. What are these lines connected to? SM rack ultimately goes to CPU. Maybe it's just easier to do this. But there's a M rack way down there. These are L, these are not used lines. If I can, I will stay away from the prototyping region because who knows what I'm going to do on this region, right? I may need to cut traces, I may need to use some force during soldering, all kinds of stuff. That means there can be a damage to traces that are close to it. So that's just because I don't have any experience. And I have to consider everything that I can think of as it may happen. Maybe it's like this is enough clearance, or even this is enough clearance that I'm not going to cut the trace while like brute force soldering some component with like massive heat mass, maybe like a a voltage regulator or something here. But you know what? It may happen. And yep, I'm ignoring my own advice by routing a long horizontal wire here. And that thing goes there. I may have to get close. Or I may have to get off grid. You know what? I'm choosing to just use a smaller grid. I've set the constraints on this KiCad instance that like if I place two lines as close to each other as possible, they'll be on a 0.02 inch grid. So yeah. But I think that's it for today, guys. I'm going to end the stream right now. I have routed enough parts. I tackled some part of the protection circuit, some part of the memory circuit. Most importantly, this bus, I wasn't sure whether I could do it within the sockets, but now I've proven that I can. Maybe I don't need to do that, but yeah. One little bit of trivia. The 0.02 inch like wire spacing is the same I found on a PC88 from NEC that is manufactured in something like 1982. So none of this board have violated that constraint. Of course, this is a Vera header, which wasn't available back in 1986, but you can connect the TMS 9918 to it. And all of the components were probably available back in 1982. Did I say 1986? I mean 1982. So, if someone was crazy enough to have the idea back in 1982, they probably could have done this. The problem is, I think there is a wait state that cannot be generated fast enough with standard TTL logic without going to like F series or like ALS or AHC series, basically the fast series of gates. If you don't use those, you cannot clock the CPU higher than probably 2 megahertz. If you are lucky, you maybe can do it with 4, which is pretty fast in 1982. Almost everything back then, like the MSX, the ZX Spectrum, almost everything back then have 3.58. Basically the NTSC color burst. Or 3.54. I think some of them have 3.54, which is like 4/5 of PAL color burst. PAL color subcarrier frequency. So that is that. If you run it as 3.58, this thing is a 1982 computer. Except people back then in 1982, they will not design the motherboard as an M80X. But yeah, that's it for the stream. I'm Andy and I will see you in the next one. Bye.